before we get going. Today, in section 2.4, let's remind us a little bit of what we've done so far in chapter 2 and what our goal was for the end of, or by the end of chapter 2. So we started by introducing a new way or an additional way to measure an angle called the radian. So now we have these two different methods of measuring angles, radians and degrees. In section 2, we reviewed our right triangle trigonometry techniques. In section 3, we developed a new way to draw angle of any size, positive or negative, as big as you want, as small as you want. We called that the standard position angle. We had the initial side on the positive x-axis, and then we rotate either clockwise or counterclockwise with our pivot point at the origin, depending on whether our angle was positive or negative. We call that other rotating arm the terminal side. And our goal for chapter 2 was to break free of our geometry definition for sine, cosine, tangent, etc., that was tied explicitly to right triangles. We want to break that definition so that we can do sine, cosine, tangent, etc. of angles of any size. Now that we are able to draw angles of any size, we are ready to do that. And that's our goal today. So we're going to see two new additional definitions for sine, cosine, tangent, etc. We're going to see those two additional definitions today. All right, let's get going here. So let's start, and we're going to start with an angle in standard position. So I have my initial side, and then I have my terminal side. I'm going to call this angle alpha. So that's that little fishy symbol is the alpha symbol. A reminder in trigonometry, oftentimes we're going to have like, excuse me, or bless you. We'll have variables going on for coordinates and side lengths and angle measures, and it gets a little bit confusing about what variable can go with what. The convention typically is, in these cases, to use the Greek letters for our angle measures. So that fishy symbol there is the Greek letter alpha, as in like from religion class, like I am the alpha and the omega. That's the first and last letters in the Greek alphabet. So we have our standard position angle here, angle alpha. And let's pick some point on the terminal side of that angle. I'm going to call that point P. And let's say that it is the point just x comma y. So far, so good. If we look at this, I can use that point P to kind of draw in a right triangle into this situation, right? You guys can see that? What should I call this side length of my green triangle? What symbol should I use to represent that side length? What? A? No. B? No, no.
Sigma.
No.
Alpha?
Omega.
Let's ask this question, okay? We have this point P that we plotted, right? Describe to me how we plot a point. If I plot the point 2, 3, how do I do that? Go 2 over and 3 up. So if I'm plotting the point XY, I'm going to go x over, right? And then y up. Do you guys see that? So look at what we've done. We've tied the side lengths in this right triangle to the coordinates of this point P. You guys catch that? Now the third side of this green triangle here we're going to call R. What can I say about R? Well, X, Y, and R. What can I say about X, Y, and R? We're in a right triangle. We can use the Pythagorean theorem. That's exactly right. So R squared is equal to X squared plus Y squared, or R is equal to the square root of X plus, or X squared plus Y squared. Now, if we look at the angle in red, what is R representing? In the green triangle, R is the hypotenuse. But what about the angle in red? What is R representing? R is the distance from the origin to that point P. Do you guys see that? That R is just the distance from the origin to that point P. And you know what we've just done? We've just translated our right triangle definition for sine, cosine, tangent, etc. from, or into, or I should say onto, a point on the terminal side of an angle. So, for example, I know that sine alpha is like opposite over hypotenuse. And in our green right triangle there, opposite is y and hypotenuse is r. Everybody see that? But without that green right triangle, y is just the y coordinate of that point P, and r is just the distance from the origin to that point P. None of that stuff was dependent on a right triangle. We can do a similar translation for cosine, tangent, secant, cosecant, etc., which gives us now oops, that's a typo. New definitions for sine, cosine, tangent, cosecant, secant, cotangent in terms of the coordinates from P, or the coordinates of P, that point on the terminal side of our angle, and R, the distance from that point P to the origin. This new set of definitions is really important. You'll use these a lot. the expectation is that you'll have these memorized, and you're like, oh, dear Mr. Kulik, really? And I will say to you, student, relax. You already have these memorized. This is just SOHCAHTOA, where opposite is the same thing as y, adjacent is the same thing as x, and hypotenuse is the same thing as r. This is just SOHCAHTOA again. We've just translated the sides of the right triangle into coordinates of this point P and the distance from P to the origin. Oh, well, that's not so bad. I like it when it's just the same thing I already know. Right? If I look at cosine of alpha, that's x over r. X is really the same thing as adjacent. R is the same thing as hypotenuse. It's just SOHCAHTOA again, right? Oh, yeah. I'll take it, Mr. Kulik. I'll take it. All right, let's do an example now. So it says the point -3, 4 lies on the terminal side of angle theta. Find the values of all 6 trigonometric ratios for angle theta. Well, I'm going to take a moment and just kind of draw a picture of our angle theta. You don't really need to do this, but I think it helps in the beginning while you're still kind of getting the hang of things. So I'm going to start by drawing my xy axis, my initial side on the positive x-axis, and then I'll plot the point -3, 4. Everybody's cool with the picture I've drawn? So that's our angle theta. No big deal there, right? Okay. So if I look, the x is -3, the y is 4, but we don't yet know what r is, because I know with x, y, and r I can define all 6 of my trig functions, right? So I'm going to have to calculate r for starters. Everybody's good with, like, the x just came from the x coordinate and the y just came from the y coordinate, right? Who remembers our definition for r in terms of x and y?
R is the square root of x squared plus y squared.
Great. And remember that it's a distance, so it's always positive. So let's see, when I plug in -3 and +4, -3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and the square root of 25 is just 5. Everybody okay there? And now I have everything that I need. So I know sine theta is y over r, so that's going to be 4/5. Cosine theta is x over r, so that's going to be -3/5. And tangent theta is going to be y over x, that's going to be 4 over -3. Everybody's good with how I plugged those in? No big deal, right? Now, remember, sine and cosecant are just reciprocals, right? And cosine and secant are just reciprocals. And cotangent and tangent are reciprocals. So I don't actually even really need that definition for those guys. I can just, again, use the fact that they're reciprocals. I mean, I certainly could have done cosecant as r over y. But if it's just the reciprocal of sine, I already wrote down sine. Why would I just write down the reciprocal, right? Seems easier to me that way. What do you guys think? It's okay so far? What do you notice about our answers for some of these sine, cosine, tangent, etc. that has happened here that we've never seen happen before? Yeah, we got some negative answers. Woo! That's okay, right? That's okay. And in fact, those negative answers are perfectly predictable. Let's talk about how to do that. So let's predict when we're going to get negative answers here, or positive answers. It's kind of the same. If it's not negative, then it's positive, right? So I'm going to draw a little picture to help us explain how to do this. So in the first quadrant, any point in the first quadrant, its x-coordinate is positive or negative? Positive. And any y-coordinate in the first quadrant is going to be positive. And r is a distance, so that's always positive. So everything, sine, cosine, etc., is going to be positive in the first quadrant, right? So those are all greater than 0. I'm going to write an A here for all So I know all of our trig function are positive in the first quadrant because, well, all of our x and y coordinates are positive in the first quadrant, right? In the second quadrant, the x's are positive or negative? Negative. The y's are positive. So any trig function that involves the x coordinate is going to be negative. Everything else will be positive. So sine is positive and cosecant is positive, but cosine, secant, tangent, and cotangent are all negative. I'm going to write an S in this quadrant to remind me that sine and its reciprocal are positive in that quadrant. In quadrant 3, x is and y is. So anything that involves just one x or y is going to be negative. If they don't have any x's or y's, or have to have an x over a y, then they'll be positive, right? So we know that tangent and its reciprocal are positive, but everything else is negative. So I'm going to write a T for tangent in quadrant 3. Again, reminding me what stuff is positive is what my letters are doing. Since there's only, like, other than quadrant 1, there's only 2 things that are positive in a quadrant, right? Everything else is being negative so far. Let's see if that holds. Quadrant 4, x is positive, but y is negative. So anything with a y in it is going to be negative. Anything without a y is going to be positive. So I know that cosine and secant don't have any y's in them. Those will be positive. But everything else will be negative. Bless you. You're welcome. And so I'll put a C down here for cosine. So the way that I was taught when I was in your seat, long time ago, the way that we remembered what stuff was positive, we used the acronym All Silly Turtles Crawl, where the A was short for all. In quadrant 1, everything is positive. Silly was for sine. In the second quadrant, sine and its reciprocal were positive. Everything else would be negative. Turtle, T is for turtle. Tangent, in quadrant 3, tangent is positive and its reciprocal. Everything else is negative. Crawl, C for cosine. In quadrant 4, cosine and its reciprocal are positive, but everything else is negative. So, again, what many moons ago I would have said all silly turtles crawl was the acronym, or it's not an acronym. What's that, like a mnemonic device for remembering? Yes, Max. Absolutely. Certainly. Is everybody so far so good? Okay. Let's do a different kind of example. So let's say we want to find cosine of 150 degrees. Now, can we do this using our right triangle definition? No, because you can't have a 150-degree angle in a right triangle, right? So we're somehow still going to have to be using our new point definition. But it's not exactly clear what point we're going to be using because all they give us is an angle measure, right? Well, let's start by drawing a picture. It's got to be some way of doing this. Maybe if we draw the picture, it'll become clear to us. So I'll start by drawing my XY axis. We'll make a standard position angle, so the initial side goes on the positive x-axis. We'll rotate from there 150 degrees. So we have 90 degrees for the first quadrant, and then like 60 degrees more. And so I know this angle down here is 30 degrees, right? Is everybody cool as to how I was able to figure all those things out? Okay. So I'm going to say, let's pick a point here. That'll be my point P. Anywhere on the terminal side will be fine. Just like before, I'm going to make a right triangle out of P. And wait a tick. That's a right triangle with a 30-degree angle. What's the other angle in that right triangle have to be? 60. That's a 30, 60, 90 triangle. Great. So I know the side lengths, or the ratios of side lengths for a 30, 60, 90 triangle. That's A root 3, and then 2A. Does everybody feel okay so far? So what does the value for x then have to be?
Negative.
So it has to be negative, great. And I remember that to plot that point P, I would go left A root 3. So that's going to be negative, more space, A root 3. And then what's the y going to be? Positive A and we know r then has to be 2A, right? Since r is the distance from the point to the origin, we know the hypotenuse is 2A, so that's the length as well. Everybody feel good? So we know that x is negative A root 3, y is A, and r is 2A. So cosine of 150 is just going to be x over r. So negative A root 3 over 2A, which reduces to negative root 3 over 2. So if I ask you to find sine, cosine, tangent, whatever, of some angle using our point definition, the only way that you're going to be able to do that is if it turns into like some 30, 60, 90, or 45, 45, 90 triangle, right? And like that just inherently has to pop out of it. Now I'd like to take a second here and backtrack to a very important thing that we did and happened real fast, and Roman was right on it. But it is will you grab the door for me? It is a super duper common mistake, and because it happened so fast, I want to point out what happened here, because it's, I would guess that the first time doing things like this, 2/3 of us will make this mistake. The thing I want to point out to you is that negative sign. Why did we put that negative sign on the A root 3? Roman did it, and he did it real fast before I even really, he gave me an answer I wasn't expecting to get already, but it was the correct answer, so he just went with it. But why did he put that, know to put that negative there? Roman, you want to tell us?
Because the x was negative on that side.
Great, because since the point is in the second quadrant, we knew on the left side of the y-axis, all the x's are negative. We may put that negative sign there for a geometric reason, right? Not an algebraic one, a geometric one. This is hard. One of the things that can make trigonometry difficult, because we have things that we'll do for geometric reasons and things that we'll do for algebraic reasons. And we got to look for both of them. So I'm going to make a big deal here on this and make sure that I'm really reminding you that to get whether things are positive or negative, you have to look at where it's at on the x and y axis. Right? Think to yourself, is the x or y coordinate positive or negative here? and make sure that you're looking at your picture. Without the picture, I don't know if we catch that, right? The picture is super duper important. Does everybody feel okay here? Okay, have I made a big enough deal about this yet to where hopefully we remember? Okay, very good. So there's one improvement we can still make to what we've done so far. In this previous problem we just did, we had a choice somewhere. What did we choose that we could have made a different choice at? We chose the location of P. Now, P was on the terminal side, but it could have been anywhere on the terminal side. By choosing P in a standard way, we can make this process even a little bit nicer. Yes. So the way that we're going to do this, the way that we're going to standardize this choice of P, is we're going to select P so that the distance from that point P to the origin is always going to be 1 unit in length. So a question for you guys. If we take all the possible angles and we take the P that's 1 unit from the origin from all the possible angles, what shape do all those P's make? If I plotted all the P's for all the angles, all possible angles, so that the P's were 1 unit from the origin, what shape would those points make? Valentina, what's the answer? It's a circle. That's correct. I called on her because she drew it with her finger. I think because she had a mouthful of cookie. You're fine. You can eat a cookie. This circle has a special name. We call this the unit circle because the radius for that circle is unit length. Its length is 1 unit. So, what does that allow us to do? If we take our definitions, our point definitions from before, but now we set r equal to 1, what does sine alpha become? If we replace r with 1, sine alpha just becomes y over 1, or just y. So we can do that now. Right? Try it again. If we do that now for all of our trig functions, we have a new set of definitions. This would be our unit circle definitions. I call this the point definition. We have our unit circle definition. And then we had our right triangle definition. Which was just SOHCAHTOA. So we have these three different definitions for sine, cosine, and tangent. Throughout this course, you will be going back and forth using these different definitions. Okay? So part of the challenge will be selecting the right one to use, or what's most convenient to use. But oftentimes, as is frequently the case in mathematics, there's a lot of ways to skin a cat, so to speak, where you might be able to use any one of the three definitions depending on how you kind of get to it, and it still might work. Now, recall, throughout the homework, we've been periodically asking for exact values, specifically for sine, cosine, tangent, and etc., right? That's been a homework question that's come up over and over as an example problem, or in the homework, or in the Delta Maths, or whatever, right? That's something we're frequently interested in. What we are going to do is we acknowledge that, like when we did this cosine of 150, if our angle that we draw makes either a 30, 60, 90 or 45, 45, 90 triangle with the x-axis, we're going to end up in one of these situations where we can find an exact value. Okay? What we've done as mathematicians is we've taken a circle and embedded that information onto it. What you're looking at right now is the units, what we call the unit circle, where at 30-degree angle, the x-coordinate and y-coordinate for our point P are given. Now remember, from our definition, that we just gave, the x-coordinate is the same as cosine theta. And the y-coordinate is the same as sine theta, right? And tangent is y over r. So with this, we can calculate really quickly and easily sine, cosine, tangent, etc., and get the exact value for anything at this point that we can reasonably ask you to give. So if I asked you, what is sine of 210? Well, I'm going to locate 210 degrees on the unit circle, and I remember that sine is y on the unit circle. So I locate the y-coordinate and say, oh, sine of 210 is -1/2. That's it. Mr. Kulik, that was so fast. There's like nothing for me to do. That's the point of this, is somebody's already done the hard work and kind of collected the exact answers to these problems that we can get exact answers for and put them on one place for us just to look up. It's like a table of values almost, except instead of being columns, it's a circle. Yes, Anthony? Not in this class. What if I had asked you, say, for cosine of 405? If you look at this, you're like, wait a second, Mr. Kulik. there's no 405-degree angle on this thing. I go, you're right, there isn't. But is 405 coterminal to an angle on this thing? Yes, it is. Right? 405 minus 360 is 45. That I see right there. Cosine of 45 then is root 2 over 2. Done. Ooh. Mr. Kulik, I like this. This is fast. Do you need to get good at using the unit circle? Absolutely. This will be a regular part. Using the unit circle will be a regular part of this, I would say, every subsequent chapter in this semester. I will have for you next class a physical copy of the unit circle that I will hand to you, so you don't have to keep referencing this page on the content library, although if you lose yours, it's there for you. Or if you're just like, I live in a digital world, Mr. Kulik, like give me the digital version, I don't want any of this paper stuff, it's there for you. But I will give you a paper one anyways, you have to take it. You recycle it on your own, just don't let me see you do it. Okay? I understand that. Do we feel okay about this unit circle? We'll get a lot more practice using this. Okay, this won't be the only examples we do of you guys using it. I have one more example problem to show you guys, and then we can be done for today. Sound good? I think it sounds good. All right. This last example says find sine theta if cosine theta is 5/7 and cotangent theta is less than 0. This is like a 3-step problem. Okay? The first thing I need to do is I need to locate what quadrant my terminal side of angle theta lies in. So since cosine theta is 5/7, I know that means cotangent is positive. Cotangent theta is negative. Well, I know that also then has to be true for tangent, because if a number is negative, its reciprocal is also negative, right? Everybody's okay there? So if I go back and I look at my all silly turtles crawl, cosine is positive in A and C, all and cosine, so it's negative everywhere else. Tangent is negative, or I'm sorry, tangent is, I did the wrong thing, sorry. I know, I'm sorry. Just put an X and draw it again, it's to be okay. I had it reversed. My thing says cotangent, or says cosine is positive, right? Cosine greater than 0. I should have highlighted quadrants 1 and 4, right? Where all and C, where cosine is positive. Tangent is positive in A and T, so it's negative in C and S. What quadrant does my angle lie in then? Quadrant 4, where both are true. Is everybody so far so good? So I'll draw my picture then. and I'm going to be using the point definition. So I'm going to go back to my given information. I'm told that cosine of theta is 5/7. I remember in my point definition that cosine is x/r. So I know x is 5 and r is 7. Now I need to find y. And once I have y, I can answer any question that you want about angle theta, right? What can I say straight off the bat about y? It's negative, right? We're in the fourth quadrant. We're below the x-axis. I know that y-coordinate is negative. Let's figure out it's negative what? I know that r squared equals x squared plus y squared. So 7 squared equals 5 squared plus y squared. Everybody's okay there? Just the Pythagorean theorem, right? That was one of those definitions at the beginning that we boxed up. The formula we'll use over and over and over again. 7 squared is 49. 5 squared is 25. I subtract 25 from both sides. I get 24. If I square root 24, or square root both sides, get the y by itself. Square root of 24 is 2 root 6. I simplified that in my head. If you have to write that down, please write that down. It's not an expectation that you're able to reduce radicals in your head. I'm a math teacher. I can. It's not my expectation that you will yet be math teachers. Maybe some of us in the future, though. We can dream, right? Again, to do that, 24 is 4 times 6. So the square root of 4 is 2, and then we have the root 6. So if we want sine theta, sine is y over r. So that's 2 root 6 over 7. And I'm done. So the steps are, we figure out which quadrant the terminal side of our angle lies in. We solve for the missing x, y, or r, whichever one that is. And then we plug our stuff into our formula to get our final answer. It's like 3 steps for that kind of a problem every time. Questions so far on what we've done today? Great. This is my plan. Today, the homework I'd like you to work on involves doing the point, using the point definition. So that'll be problems 45 through 50. And then I have a delta math for some additional practice, doing some of the skills we worked on here the first part of class. Next class, we'll be doing homework working on the unit circle definition. So that'll be 51 through 60, and then I have a worksheet for you to work on. Does everybody feel okay with that plan? Let's look at the delta math problems, just so we can see the instructions there. My suggestion for you would be to do the delta math first, because you get a lot of feedback from that about if you're doing stuff right or wrong before doing the book problems, but that's up to you. So there's a new delta math, chapter 2, delta math 3, not due till Sunday at midnight. And these are the kinds of questions we're asking. So it says, okay, what quadrant does theta lie in if tangent is negative and cosine is positive? Well, that has to be quadrant 4, right? Cosine is positive means it's to the right of the x-axis or the y-axis, and tangent's negative only when either x or y is negative. And quadrant 1, they're both positive, so it has to be quadrant 4. So I'm just picking the quadrant. Next one is the same idea, but you might get things that are not sine, cosine, or tangent here. You'll get secants and cotangents and stuff in here now also. Next one is just like that last problem I gave you, except they've cut out step 1 because they're telling you the quadrant. And in fact, on this first set, I think they're all in, it's always in quadrant 1, so you don't have to mess with negatives and positives, since we know everything is positive in quadrant 1. The next set is just like the final or the last example, except they're telling you the quadrant. Here it could be not quadrant 1, so you have to be careful about signs on your x's and y's. The third version, same idea. They're going to tell you the quadrant, but they're going to give you like some of the reciprocal ones are mixed in here too. Again, not really different than what we just did. In fact, it's an easier version of what we just did. This is just like the example, or the first example we did for the point definition, right? Where I just give you the point and ask you for the value of, in this case, cotangent. And then our last one asks you to draw the picture and then find the, in this case, sine theta using the point definition again. Just like that first example we did. Does everybody feel okay with what we're asking you to do? Not too bad. So you guys take the remainder, the last half hour, 40 minutes, or whatever's left here, to kind of get through that stuff, or get through as much as you can. If I'd emailed you about your homework, like you turned something in a funny way and I wanted to make sure that we can actually get it into your OneNote, I'm happy to take care of that now if some people want to come and do that. Otherwise, you should be working on either your Delta Math or your 44 through 50. The order in which you start is either way is fine with me. I would suggest the Delta Math first, where you're getting some feedback before you dive into the problems where you get a little bit less feedback. Okie dokie.